So hi everyone, I'm Aanand, I work at Docker. I'll just do the first part of my talk while my laptop restarts. It seems to be complaining because it was connected to hotel Wi-Fi, which as we all know is a terrible idea. So I work at Docker. I work on a tool called Docker Compose. Some of you might have heard of that or use it. Does anyone use it? Nice, cool. Does anyone remember when it was called Fig? Nice, all right, you're my friends. If you want, come and find me afterwards if you want a Fig sticker. They fit very neatly over the Apple logo on your laptop, which is cool if you like the idea of replacing one fruit with another. So what I do is, like, I used to be a software developer who made like apps that go on the internet and have to scale and stuff. And now I do something weird and kind of like a meta version of that, where I don't make those apps anymore, but I make the tools to make the apps with. Or I make the software for deploying the software, or I make the software for developing the software. And that is weird, but it's also incredibly interesting because it means that the engineering challenges I have now are, okay, you'll restart again, fine, okay, that's fine. Computers are good. Great, yeah. So now I have a completely different set of challenges, and a lot of that is like hypothesizing and theorizing about the challenges that people who actually do make apps have, and then trying to solve those problems in a general sense, or rather empower people to solve those problems in a general sense. So like that's really weird. What I'm going to talk about today is, like, you'll probably see a lot of talks about like how to build apps for scaling and that kind of thing. The thing is, I don't do that anymore. So instead, I'm going to share insights from my job, where my job is mostly building the kind of meta software that like helps you build the software. So what that means is that I face a completely different set of challenges. All right, let's see if this works now. And so basically I'm going to share some insights and some lessons from oh wait, that's from wrong conference. There we go. Right. Cool. All right. So I'm going to share some lessons that I've learned from working not on apps, but like on tools to make apps. So the potentially controversial thing I'm going to start with is that like this conference is all about scaling, which is weird to me because to me like scaling should not be like it should be an implementation detail in the sense that, like, the difference between small scale and large scale, or the difference between development and production is real. It's extremely real. If it wasn't real, we wouldn't be here. But they are conceptually, I posit, the same thing. It's all just running programs on computers. How hard can that be? Like, okay, sometimes the computer is a laptop, and sometimes the computer is a blade server, and sometimes the computer is 1,000 blade servers. But like, it is basically the same thing. And so I hold out hope that we might, get to a point where scaling is really just dragging a slider, because that's what you want your job to be, dragging a slider to the right. Like, your app is changing dramatically by the week, probably. That's just how it goes in our industry. You'll move faster if you're not coupled to the implementation of how it scales. If that implementation is easy to change and decoupled from like how your application works, you're going to have a better time. And when your app gets to the front page of the orange website, you don't want to be like hand provisioning servers or some nonsense like that. You want to be dragging a slider to the right. So like the software that I work on, like broadly speaking, is about helping you get to that point. And So like my job consists of three things, at least. There's more than this, but like my job used to just be writing code. That was how I primarily thought of myself. Like we actually like call ourselves coders sometimes, as if the code is the most important thing about what you do, when really it's kind of incidental. But on top of that, what I do today is a lot of open source maintenance, and I design abstractions. So we all have an incredible number of opinions about writing code, and I'm not going to throw any of those at you today. We probably have quite a few opinions between us about how to do open source maintenance, and I'm also not going to talk about that today, even though I could for a while. I'm going to talk about designing abstractions, partly because I think that is a really interesting thing, and I think it is something that we don't talk about a lot, even though it's like incredibly important. So this is a talk about abstractions, and I'm going to structure it as follows. I'm going to do a couple of rounds of this, wherein I show you an abstraction that we designed that didn't really work, and then what we replaced it with, and then hopefully we can extrapolate some kind of insight from that. So we make software that, like I say, kind of broadly speaking, one of its goals, I mean, aside from like being the thing that you use to run everything all the time, everywhere, is to abstract away the idea, like the specifics of scaling. And so, much more specifically than that, what our software does is, well, run containers. You have containers built from, you have images that you can pull from somewhere. You can start containers from those images. You can get those containers to talk to each other. You can get them to store data. You can get them to listen on, like, you know, for network traffic, and you can get them to communicate and like serve your website to the outside world and whatever. And you know, the idea is that everything eventually will go in a container, and they'll become your application will become portable and more decoupled and better structured as a result. And so the first abstraction I'm going to talk about in this model is how you get containers to talk to each other. And the original abstraction that we designed for that was called links. A link being a very simple thing. You have two containers, a web server and a database, and you have a link, which is a one-way connection between them. So you have a one-way connection from the web to DB, which means that web can connect to the database and get data and write data. So a link defines two things: reachability and discoverability. The ability to connect to another container at a particular IP address, not one that you've specified, just some IP address, and the ability to look up that IP address by a host name, which makes it sound more complicated than it is. All the abstraction that we're presenting to the user really says is, yeah, you can connect to db:5432 and start speaking Postgres to it, or whatever you want to. So like, the process for creating a link is very simple. You create your database container, your like upstream dependency. You create your web container with a link to the database container, and you specify a name that you want to connect to, and you're done. Like, your web container can now connect to the database at that particular host name. Very simple. I'll just demonstrate it now, assuming my computer still works. So let's see if this works. Oh, yeah. So, is my Docker server still running? Yeah, lovely. So, like, I'm just going to create a container. Oh, don't have it. I'll give it a name. I'm going to run it in the background, and it's just going to be a dummy thing. It's like, I'm just going to run the top command, just so that I have something long running. Okay, so I've got a container running. Great. Now I'm going to run another one. I'm going to make it interactive. It's going to link to the DB container, and I'll just open up a shell. Now, in that shell, I can go ping DB. Brilliant. That's how links work. It's very simple. And that used to be like our primary way to get, like communication going between containers. For quite a while, we thought, this is fine, we're going to stick with this, and we're going to improve it. We're going to make links dynamic so that you can add and remove them at runtime without destroying or recreating containers. We're going to make them work across multiple hosts, so your web server can be over here and your database can be over there, and everything will just work. They'll still be able to privately communicate. But we didn't do any of that because actually they're a bad abstraction. They're a poor abstraction over the idea of scale. Because what happens as soon as you go from one database container to two? What are you linking to? Which one are you going to link your web container to? You could say, all right, I'll just pick one. Cool, all right, everything works. What happens when that container dies? Does the web container die too? You probably don't want that to happen. So in this world where we assume, we've made links dynamic and you can change them anytime, I guess it's your job as the consumer of this abstraction to detect that condition and to point that link somewhere else to the other database container. Okay. Instead then, I'm going to connect to all of them, and then my web container will load balance over them. Cool. That will also work. You don't have that problem of having to fix it in some kind of outer layer when one container goes down. But now you've got to remember to add a link every time you add another database container. It's not too bad, but you also need to add n links every time you add a web container, and that's a lot of links to worry about. So there's the problem. This just doesn't scale. We've got a x times y problem, which is not something you want to have. So here's the first, and it's probably a fairly obvious lesson. If the abstraction itself doesn't scale, then you failed at creating an abstraction over scale. So that's why, that's why links didn't end up getting turbocharged and improved with loads of functionality, because they just weren't they worked in the small case, but they're not going to work as soon as you have a remotely serious app. So we deprecated them. They still work, as you can see. You can still use them, but they're not the recommended way to do things. Instead, we have networks. A network, rather than being a one-way connection from one container to another, is a long-lived thing that just sits there, and containers, which come and go, can connect to it. It's still conceptually very simple, and we've worked hard to make it conceptually very simple to use. So the process is, well, now you have to create a network first. Then you create a database container, and you say, I want to connect it to this network with this particular name. And then if you create another container, a web container connected to the network, then the web can now connect to the database. It's almost the same thing, and I'll demonstrate it really quickly. So close that. If I go, shall I make this bigger? I'll make this bigger. I'll just create a network here. So I'll say I'm going to create a new container. I'm going to connect it to that network I just created. I'm going to give it the alias db. And again, it's just going to be a long-running thing in the background. Cool. Now if I run an interactive container that's also connected to that network, and it will be a shell, then once again, I can connect to the hostname DB. Brilliant. Okay, so it's very similar, but this is a far, far better abstraction. Because now, as you increase either the number of web containers or the number of database containers, you don't have any extra work to do. You don't have like 100 little relationships to manage. Everything just connects to the one network. So this scales much better, but you'll notice that I've dodged the question of which one's talking to which. And the wonderful thing is that it's still sort of the abstraction has not dictated which one's going to talk to which, but also it's not getting in the way of that decision. The abstraction can remain the same, whatever the logic is for which web container is going to talk to which database container. In fact, in the last release of the Docker engine, 1.11, we changed the default behavior. It used to be that the DNS lookup would return a single IP address, just like if there were multiple DB containers, you look up DB, you'd get one IP address back, and in fact, that would persist for the duration of whatever container you were in, I believe. Don't quote me on that. But now, we've changed it, and the DNS lookup actually returns all of them. So if you're a smart client, you can use that information to load balance. Of course, if you're not, that's fine, and everyone's code that is currently out there continues to work because the abstraction does not get in the way. So this could never have happened with links because links got all up in the particulars of one thing connecting to another and forced you to do that work yourself, to decide how things connect. And if you ever wanted to change your mind about that, it wouldn't be a case of just changing a configuration setting somewhere and keeping everything the same. You'd actually have to go in and change your own code, which was managing links or whatever. So by I think the main thing we did that meant that networks turned out better than links was that we started from the scaled up case. We started from the many instances case and then treated the one instance case where you've just got one thing talking to one other thing as just a special case where n equals 1. So that might be the lesson from this one. But actually, it's not. I mean, it is a good thing to do. You should do it, but it's not enough. So you'll notice how when I demonstrated creating, getting two containers talking to each other with networks, there was an extra step. With links, it was 2 commands. It was create thing, link to thing. With networks, it was create network first, and then create thing connected to network, and then create other thing connected to network. And that's less simple. That's strictly less simple. If I'm a developer and I want to get my app running on containers, I don't want to learn about networks. It's just not important to me. All that matters to me is that my web can talk to my database. I don't want to have to learn a new oh, now I've got to read a page on networks. Forget that. I just want to get my app running. I don't want to know that that this is a thing that has to be done. We can't afford to lose that kind of simplicity. Maybe you can, if you're just making tools for ops people, you're just making tools for scaled up scenarios, but we're making tools for everyone, including people who are just playing around on their laptop and whose apps might never making it to large scale. They might never make it to production. They might never make it off their laptop because they're just playing around, and they should still be able to use the highest quality tools that everyone else does. So arguably then, we've made things worse? Well, actually, no, I don't think we have made things worse, because actually typing those CLI commands, that's not the simple case. That's the low-level interface to the entire tool set, and not what most people who are getting started will be using. They'll instead be using Compose, which is the thing I work on. As I mentioned, if you remember when it was called Fig, come and find me afterwards. I've got a sticker for you. But yeah, so like how Compose works is you write a configuration file, and then you type a single command. It's called docker compose up, and your app is running, which is great. So here's what that file looks like if you're using links. You have two services, web and DB. You specify an image for each one, and web links to DB. It's got a links key. Great. How do you change this to use networks? Well, you delete the links key. That's it. Because by default, we create a network for your whole app, and every container joins that network as its service's name, web or DB. So everything can already see everything else. You actually have less to think about. You don't need to know that that's happening, of course, if you're just starting out. You just know that everything can connect to everything else. So we've actually not only made the scaled up case better, but we've actually even made the simple case simpler. It's a win-win. So here's the actual lesson. Both cases are important. There's like, you can't ignore one in favor of the other. You have to, like, if you're designing something that you expect people to use, and you expect them to use it both at scale and not, then you have to cater to both. And if you are thinking right now that, like, no, people are just gonna, like, this is just for serious use, then I think you might be a little naive. It's like, everyone's like been at an organization where, like, just to get the software running, you had to install like Puppet in a VM or something like that. Like, you don't want to, like, maybe the answer there is that you shouldn't, like, you know, that shouldn't be the that shouldn't be how you get your dev environment running. But like, if you care about users, and you care especially about other people in your organization who don't know about ops and scaling and monitoring and configuration management, then like you have to cater to the small case. It's just as important. Okay, so the next problem I'm going to talk about, setting communication between containers aside, is data. Let's say I've got a database, and obviously it's got some important data in it, and I might want to destroy the container that database is running in, because I might want to upgrade the software, or I might want to change configuration, or something like that, but I want its data, obviously, to stick around when I do that. So Docker has had a solution to this from right back in the early days. It's called volumes. What you do is when you create a container, you say, I want this path to be a volume. And that's great, except that the volume still sort of belongs to the container. It's sort of like this thing that's like, it feels like like from the abstraction, you're not really sure. It's like, does this kind of live inside the container, or is it just kind of sitting around somewhere else, but it's got a link to it? For the longest time, there was no way to get at the volume directly. And that meant that like people were like, so how do I have something long running when this container might be ephemeral? I want to like throw it away and like bring up a new one. How do I hang on to my data? And that's where this pattern of data-only containers came from. So you have a container called data here that doesn't actually do anything. Its command is a no-op. And it holds on to a volume, and then you have another container, which is your actual database that's doing stuff, and that has you create it with a flag called volumes from, and that means like use the volumes from this other container. And then like now you have long-lived data but like ephemeral code. And so like your database can go away, but the data sticks around, and then you can create another database container, and like everything's fine. But like just explaining this like makes it sound annoying. Like even before you've scaled up, like this is just weird. Why can't I just create a volume independent of any container? That's what I care about. Like why am I like it feels like a hack. It is a hack. And it gets worse. It's like I'm going to multiple hosts now. Let's say I've got 3 hosts. Do I have to worry about where my containers are? Like, does my database container have to be on the same node as the data container? What happens if that host dies? Have I lost my data? It's not. None of this is clear just from looking at the abstraction or from reading the documentation or using the CLI. Like none of it is obvious. And in the old world, like sometimes the answers to these questions was, it's complicated. Or sometimes the answer was just not the one you wanted. It was like, oh, yeah, sorry, you're going to lose it. And like that's no good. So clearly the wrong abstraction here, which is why we brought in volume management and volume drivers. So now volumes are a thing of their own, a top-level concept, independent of containers. And also, the storage system for them is pluggable, which means that if you need to share data across hosts, which it turns out is a very complicated problem, there's a whole bunch of drivers available to plug in depending on your needs. There's drivers for NFS, for GlusterFS, for Open Storage. Microsoft have one for Azure. Cluster HQ have Flocker, Rancher have Convoy, and so on. There's loads and loads. The point is that you can swap in a driver, but like volumes just behave the same. Like the abstraction is the same, the API is the same, the commands that are the same. Not like either way. And most importantly, like they're not coupled to hosts anymore. Like if you have a data volume and you've plugged in a driver that like makes it available to multiple hosts, however that works, then like your volume is now independent of any specific host. If that host dies, then you can start up a new container, run your database on it, and like the volume driver will make it available. So like this is far, far better, obviously. And there's an analogous lesson here, I think, about how in the same way that the link abstraction was designed in a world where you are only ever connecting together a small number of containers, the volume and like data volume abstraction was designed in a world where you were pretty much like usually running on one host. And so perhaps the lesson here is to treat the multi-host as the default case, like, and then the single host is just a special case where n equals 1. So like, if you start, if you assume that we're on a cluster and you can't just like, things won't necessarily be co-located and they can't share data and all of that, then the single host case is just like a special case of that. It doesn't really matter, just n equals 1. And like, yeah, true, you probably should do this, but that's not the lesson. Because like I say, it still has to be really, really easy to get started. If I'm a developer and I'm trying to get my app running, I don't want to do extra thinking. I don't want to read extra documentation, learn extra concepts for the sake of some multi-host scenario that I'm never going to see. Like, I'm working on an app. I don't expect it to be, like, to necessarily become some huge clustered thing, even though it might be. I don't want to think about that now. Like, I've barely started writing my code. So just as one container and many containers are important, one host and many hosts are both important. You need simple defaults. I don't have to specify a volume driver. Like, I don't have to like think about that. And if I'm using some image from the Docker Hub or from someone else which says in its manifest that it needs a volume at this path, and I don't hook a volume up to it, I'm not going to get an error. Docker's not going to be like, sorry, you can't run this, you've got to hook up a volume. No, it's just going to create one silently, because I shouldn't have to know that the Redis image like needs a volume at varlib Redis data. I just want to run a damn Redis server so I can develop my app. So, generalizing from these two stories, one thing and many things, like neither one is a special case. Like one thing sort of is a special case of many things, but it also isn't, because if you're focusing on that, then you're ignoring the context. Like, in what context does n usually equal 1? Usually, the context in which n equals 1 is a completely different context from where n equals like 50 or 100. Usually, when n equals 1, you're looking at one developer sitting, working on a thing on their laptop. And that is a completely different case. But of course, like I say, it is the job of abstraction to abstract over that difference. And I believe that it can be done, because it's all just running software. So the whole time we were designing those network and volume abstractions and the user interface, we kept both cases in mind. Every time we made a decision for the sake of making multi-host, large-scale, clustered apps easier to deploy, we looked at how that decision would affect someone who was just sitting at their laptop. And that work paid off. We now have abstractions and user interfaces that scale both up and down. But it's important to stress that that simplicity doesn't just fall out of a good abstraction. There's a temptation, I think, in programming to believe that if you just model things right, everything will be simple. If I just have the right conceptual abstract model behind this, then it'll be easy to write, it'll be easy to change, and it'll be easy for the user to use. And I'm sorry, but that's like absolute bullshit. There is no escaping like design. You have to do it. Like you don't have an excuse. Your software is going to be bad if you don't actually do UX design. You can't hope to model things right from the start in the first place. Like you can't, it's incredibly hubristic to believe that you can because you don't know how your requirements are going to change. And if you insist on forcing your supposedly correct model on users, even though it makes their lives more complicated, then like you're doing a bad job. And even if you have some wonderful, brilliant, conceptually perfect model, but it's not that intuitive for someone who's just starting out to grasp without like doing a load of reading, if they have to like learn a whole bunch of new concepts before they can do anything productive, then you're doing a bad job. Git. So like, don't get me started on Git. So like, you don't have an excuse here. You have to do the hard work. And like, I don't really consider myself a UX designer. And even if I did, like, I would consider my experience in UX design to be very limited because I mostly make tools that like work on the command line or like whose primary like way of interacting with them is like an API. I don't make stuff with like buttons and like things that like normal human beings use, you know? So like the lessons I can take away are very limited, but like from working on things like Compose and other parts of the Docker toolkit, here's what I can tell you. You have to start from the UX. You don't have a choice. Just like stop, like if your first instinct is to write some code, like stop what you're doing. Write the documentation first. You weren't going to write the documentation anyway, but I'm forcing you to do it, not only to do it, but to do it before you do anything else. And you cover both the cases at the extreme ends of the spectrum. If there's a config file involved, write the example. If there's CLI commands involved, write the example CLI session. And those things you should treat as your source of truth. You keep them up to date whenever the design evolves. Whenever it's time to make some new design decision, you come back to those and you look at your documentation, you look at your examples, and you ask, how does this affect those? And if it affects one positively, but the other one like negatively, then like think again. Like if there's a trade-off to be made, then fine. But like as we learned from the networking example, not everything is a trade-off. Sometimes you can make a design decision that is like truly win-win, that improves everyone's experience. I'll leave you with what Alan Kay supposedly said. I couldn't find a source for it, so I don't know if this is apocryphal. Simple things should be simple. Complex things should be possible. Look at your software. Are the simple things simple? Are complex things possible with it? I imagine the answer to both of those will be sort of like, sort of not really, but like it could be better. That's fine. Me too. This is an extremely hard problem. It's called design. People have been studying it for a long time. But like, look at it, seriously. I have a feeling that you're probably doing better at one than the other. So have a look, introspect, try and improve on the other. Try and get this balance like restored. Thanks.
Thank you. Thank you, Aanand. Are there any questions for Aanand? Hi. So you had a picture of a multi-tier application where you have a web layer and then the database layer where you have I think it's like the database code and then the storage. And I think, and then you're able to solve the problem of one database server goes down, right? It was on the picture. And now my next question is, how would someone design a system with a system with data storage where the storage itself, the volume itself would be redundant? So if one volume physically is fried, then there's backup. Is there a solution for that, or you just have to use a complex database system?
We drift now into into what I consider extremely far away from my area of expertise, but this but this is partly why I stick to abstractions, but I think that what you want is to the right answer might be either one of those. And what you want, I'm sorry, I'm just not an expert in databases or in clustering. What I'm interested in is finding a model, an abstraction, that allows for both without changing how you use it. I want that decision to be separated from the person using the tools, and that the abstraction can be a kind of safe thing that sits in between a person writing code. And I don't want to, I think it's reductive and oversimplifying to divide the world into dev and ops with a wall between them. But roughly speaking, this abstraction should be a conduit via which there's a person who has a deep amount of expertise in how to store data on a cluster in a heavily redundant way that is still performant and available, and someone else whose job is writing the thing that consumes that data. And what a lot of my job is striving for is finding the abstraction that sits cleanly in between those two people and gives them all the power they want. So in summary, sorry, I don't know.
Okay, thanks.
All right, any more questions in the back, Rolf?
In the network abstraction,
Yeah.
Docker actually makes a choice to make all the containers part of the default network.
That's correct.
Have you considered that in a large-scale application that might not be what you want? And how can you change the default behavior to isolate containers in their own network?
So you're talking about, do you mean the feature of Compose, where by default, a single network is created for the whole app, and every container joins that network. So that is the case that we build in, basically to make it extremely simple to get started, because I don't believe that people getting started with Compose should have to learn about networks just to get their stuff talking to, just get their containers talking to each other. But you do have full control over that. For one thing, you can specify any number of networks that you want to create in your Compose file that might not be have whatever names and properties and options that you want. And you can secondly, you have per service control over what networks a container for each service should join. So the default network will not be created if you don't use it. If in every service you're saying, actually, I want you to join foo and bar, and I want you to join front and back and load balancer or whatever, and if in nowhere you actually say, hey, if you basically have custom network configuration on every service, then Compose is smart enough to figure out that, oh, okay, you don't actually use a default network, I won't create it and I won't connect everything to it.
All right, thanks Aanand.
Thanks.